Welcome back, everyone. I have another example I'd like us to do together where we're going to try to find the volume of one of our solids of revolution using the cylindrical shell method. So let's go ahead and jump right in. So in this example, we are asked to find the volume of the solid obtained by rotating about the y-axis, the region that is bounded by the curves y equals sine of x squared, y equals 0, x equals 0, and x equals the square root of pi. So we might need to have our calculators assist us in kind of getting the original sketch of this region going. But here in blue, we have the sine of x squared curve. Y equals 0 is just our x-axis. X equals 0 is our y-axis. And x equals the square root of pi would be this vertical line going through the square root of pi. But really, those other curves are just helping us say, this region is our region of interest, the region below y equals sine of x squared and above the x-axis. And so out in the wild, you may not know which method to approach a solid of revolution volume problem with. Should we use the disk and washer method, or should we use this shell method instead? And the thing I always keep in mind to help me determine which method to try to apply is, well, I take a moment to think about how am I going to slice this thing up, and how would I find things like the radii of my slices. And so if we were using the disk or washer method, we are always going to take our slice to be perpendicular to our axis of rotation. So our axis of rotation is the y-axis, a vertical axis. If we're using the disk or washer method, that means we want to think about taking a horizontal slice, a slice perpendicular to our axis of rotation. And well, a horizontal slice would create a washer in this instance, and it would eventually require us to find an outer and inner radius, which would require us to solve y equals sine of x squared for x in terms of y, which is going to be gross, not something we want to try to do. Right away, it looks like the disk or washer method is not going to be a great approach for this problem. So let's go ahead and try to use our cylindrical shell method instead. And so now when we're approaching these volume problems using the shell method, we think about not taking a slice, and so that quick initial analysis leads us to believe that the disk and washer method is not going to be an effective approach for this problem. So that leaves us with the shell method instead. And so for the disk or washer method, we always thought about taking a slice or using strips that are perpendicular to our axis of rotation. For the shell method, we always work parallel to our axis of rotation. So our axis of rotation is vertical. Our approximating strips or our approximating rectangles are going to have to be these vertical rectangles as well. So here is what maybe one of our approximating rectangles for our region is going to look like. We can see its height is going to be given by the output of our function. Its width or thickness is some small change in x values. That's going to be delta x. And now if we rotate this vertical approximating rectangle around our axis of rotation, we can see that we are creating one of our cylindrical shells. And so now what we have to go back to and remember is that volume formula for the general cylindrical shell. And so the volume of one of our approximating cylindrical shells is given by the product of 2 pi times the radius times the height times delta r. So remember, 2 pi r is thinking of the circumference of that shell after we've unrolled it. H is just the height of our shell, and delta r is the width or the thickness of our shell. And the first thing we want to figure out and decide upon is, what is our delta r? We like to start with this first because it's going to tell us what we have to set up and integrate with respect to, whether it's going to be x or y. We've actually already discussed this a little bit. Our delta r is going to be the same as our delta x or y in our approximating rectangle. So in this case, our delta r is going to be delta x. You can remember a set of kind of rules here, like whenever our axis of rotation is vertical with the shell method, then our delta r is always going to be a delta x. Whenever our axis of rotation is horizontal with the shell method, our delta r will always be a delta y. But I think it's better to just kind of visualize your region and one of our shells to help us determine the thickness. And now that we have determined that the thickness is going to be delta x, it lets us know that we're going to have to express the other unknown quantities, the radius and the height, as a function of the variable x. So now let's just keep going maybe from right to left. Let's find the height of our approximating shell next. And well, we already kind of referred to this. The height of our approximating shell is just going to be given by the value of our function y equals f of x. And here the value of our function as a function of x is just going to be sine of x squared. All right, so the last thing we need to find, we already got our delta r and our h, is the radius itself. Remember, the radius is always the distance from the axis of rotation to the shell itself, or the approximating rectangle we are using to generate our shell. And so our radius is going to be this horizontal distance that we have to express as a function of x. And well, since our axis of rotation is the y-axis, x is describing the distance from the y-axis to any kind of point over here. And well, that horizontal distance is just given by x itself. And so now we don't always need to write this next part down, but I like to do it because it keeps me in good practice. So now we remember that if we add up all of the volumes of these cylindrical shells, so we're going to have some sum of n shells to start off with, we're going to have to look at the product of 2 pi times the radius, which is x, times the height, which is sine of x squared, times our thickness, delta r, which is delta x. This sum that we have written on the board right now is just an approximation for the volume of our solid object. But if we take the limit as n goes to infinity of our approximation, we're going to be using more and more shells in our approximation. They're going to be thinner and thinner, and so that's going to cause that little air at the top, or wherever it ends up being, to become less and less and approach zero. Long story short, when we take the limit of this sum, we get the exact volume instead of an approximation for our volume. And well, now we just have to remember that the limit of a Riemann sum like this is going to converge to one of our definite integrals. That's exactly what's going to happen here. So what are our limits of integration for this definite integral? Well, it's going to be all the x values we go through in our region of interest. Our lower x value is 0. That's going to be our lower limit of integration. And our upper x value is the square root of pi. That's going to be our upper limit of integration. Now the rest of it gets copied down in a pretty natural way. We get 2 pi x times sine of x squared. The last thing we have to remember is that when we take the limit, the delta x turns into the differential of x instead. And so now we have a definite integral set up that gives us or describes the exact volume of our solid object. Now we just have to evaluate this definite integral. And while we might see x times a trig function here and think integration by parts is the method to use, it's actually much simpler than that. We can get away with evaluating this integral just using a u substitution. We have to set u equal to x squared. That'd make the differential of u 2x times the differential of x. And well, it looks like we have just about all of these pieces in our integral. So let's go ahead and translate our previous integral into an integral in terms of u instead of in terms of x. So notice the factor of 2, the factor of x, and the differential of x all work together to become the differential of u. So those are taken care of. Next, we have a factor of pi, which is just a constant factor that'll go along for the ride. And then one of the last pieces we have to translate is the sine of x squared, but we know that u is equivalent to x squared, so that'll just turn into sine of u. Now this is an antiderivative that we can find very, very quickly, but we still have to convert our limits of integration as well. Remember, these original limits of integration, our x values, our new limits of integration have to be the corresponding u values, since that is the variable we are translating into. And so it's easy to go from our x values to our u values using this equation, this substituting equation that gives the relationship between x and u. Our u values are just the square of our x values. And so that upper limit of integration, that x value, was the square root of pi. If we plug in x equals the square root of pi into our equation over here, we get u is equal to the square root of pi squared. That just turns into pi itself. For our lower limit of integration, we get 0 squared, which is still 0. So now we have to compute the definite integral from 0 to pi of the function pi times sine of u. And well, that antiderivative is just going to be negative pi times cosine of u. And now we have to evaluate that at pi and 0 and split the difference. Well, if we plug in our upper limit of integration, negative pi of cosine of pi is going to evaluate to positive pi, since cosine of pi is equal to -1. Those double negatives cancel out. Then we have to subtract away from our antiderivative evaluated at our upper limit of integration, our antiderivative evaluated at our lower limit of integration, which is 0. So if we take cosine of 0, we get 1. So that's negative pi times 1. We're subtracting that negative pi from our first pi, and that gives us a grand total of 2 pi. So it took a bit of work, and we had to use the shell method for this example, but we have finished it. We know the exact volume of this solid of revolution is 2 pi. Welcome back, everyone. In this example, we are asked to find the volume of the solid obtained by rotating the region bounded by y equals x squared and y equals x, gotta remember that part, about the x-axis. So our first step in our process of trying to find this volume of the solid of revolution is to visualize our solid of revolution. And to get that going, we first have to visualize the region we are going to rotate around the x-axis. So our region is bounded by y equals x squared and y equals x. So y equals x is just a straight line like this, and y equals x squared is our parabola that's going to be below our straight line, at least initially, until we hit that x value of 1. And so here is our region of interest, just that space between our curve y equals x and y equals x squared. And now we're going to rotate this around the x-axis or around our horizontal axis. And so when we spin this region around the x-axis and have it fill in all that space as it goes around, what we're going to create is this kind of triangular shape with a bit of a hollow inside, but kind of a curved hollow inside. And so next we have to decide which one of our methods do we want to use, the disc and washer method or the cylindrical shell method. And it actually turns out for this example, both methods are relatively straightforward to use. And I think this is a good example to look at using both methods to see that we get the exact same answer. So let's maybe start by finding this volume using our newer shell method. And then afterwards, we'll go through this problem quickly using our disc and washer method instead. And so, well, for our shell method, the thing we have to remember to help us get set up is how to find the volume of one of our approximating cylindrical shells. And that's given by the formula 2 pi times the radius times the height times the change in the radius delta r. The other thing that's nice to remember when using the shell method is that the approximating rectangle that we're going to eventually generate our shell with by rotating around our axis of rotation is always going to be cut parallel to the axis of rotation. So our axis of rotation is the x-axis or the horizontal axis. So that means our approximating rectangle is going to have to be sliced or cut horizontally as well. So here is what one of our horizontal approximating rectangles is going to look like. And then we're going to rotate that around our x-axis, and that's going to create one of our approximating cylindrical shells. So remember, the first thing I like to find, and that I recommend always finding first when using the shell method, is your delta R. That is the thickness of your shell. In this case, and this is always true, the thickness of your shell corresponds to the thickness of your approximating rectangle. That's going to be some small change in vertical y values. So now our delta R is going to be delta y. And what that informs us of is that we're going to have to express all these other quantities, the radius and the height, in terms of the variable y. So let's go ahead and find the height next of our approximating rectangle, which is going to correspond to the height of our approximating cylindrical shell. And well, the height here is usually what we describe as like the width, right? This change in this horizontal distance. And when we're thinking about finding the height as this change in a horizontal distance, it's nice to remember that the height, this is similar to what you did for your discs and washers or your washers, is that the height is always the farthest most or biggest x value, the rightmost x value, minus the leftmost x value. But the problem we have here, we don't want to leave it like this because it's not useful for several reasons, but the big one is it's not written as a function of y. And so now what we have to do is express that rightmost x value as a function of y, and then we'll have to subtract away from that a similar expression but for that leftmost x value. Well, as we change our y values, these right and leftmost x values are going to change as y does. And so we can recognize that that rightmost x value corresponds to a point on our parabola y equals x squared. But we have to express that point in the opposite order. Instead of having this function expressed as a function of x, we need to solve it for y, and x can be expressed as the square root of y. So our rightmost x value is going to be the square root of y, or y to the 1/2. We'll write it like that to make integration easier. And our leftmost x value is going to come from this far left point on our curve or our region, and that is actually corresponding to a point on our curve y equals x. And well, that's a really nice function. It's expressed simultaneously as a function of x and y. So our leftmost x value is just going to be y itself. The last thing we need to find is the radius. And the thing to keep in mind when trying to find this expression for your radius is that the radius is always going to be the distance from your shell or your approximating rectangle to your axis of rotation. And so our axis of rotation is the x-axis. Our shell is this horizontal shell or this horizontal rectangle, and the distance from that horizontal rectangle to the x-axis is a vertical distance. The vertical distance is exactly the same and corresponds to whatever y value we are working with. So our radius here is just going to be y itself. And so now I'm going to skip right in all like the limit of the sum part. We know that our volume is going to be given by the definite integral of 2 pi r times h times delta r. Well, 2 pi times r is 2 pi times y. Our height is this more complicated expression, the difference between the square root of y and y. And then we have to multiply that by delta r, which is delta y, but we have to remember in the integral, we've taken the limit, and the delta y becomes the differential of y. The last piece we need to finish setting up our definite integral are our limits of integration, and these are going to be all the y values we go through in our original region before we rotate that region. And so our lower y value is 0, and our upper y value is positive 1. And so our goal for this problem is to find the volume of our solid of revolution, and really the hard part of that process should be setting up these definite integrals. Once we have them set up, they end up usually being pretty straightforward integrals, so I'm going to kind of move quickly through these integration steps. So the first thing we should do to actually integrate this function is expand it. So 2 pi y times y to the 1/2 is the same as 2 pi times y to the 3/2. Then we have to subtract away from that 2 pi times y squared, just distributing 2 pi y to each of our factors inside of our parentheses. And so we have to increase our exponent by 1. That'll make it 5/5. And then we have to divide by that new exponent of 5/5, which is the same as multiplying by the reciprocal, the same as multiplying by 2/5. So that'll give us 4 pi over 5 times y to the now 5/2 as the antiderivative of our first term. And for the antiderivative of our second term, we're again using the power rule, but this time it'll end up looking like 2/3 pi times y cubed. And so now if we evaluate that at our upper limit of integration, the y value of 1, and subtract away from that our antiderivative evaluated at the lower limit of integration at y equals 0. Well, y equals 0 doesn't contribute anything, so we just end up really with 4/5 pi minus 2/3 pi, and that works out to exactly 2 pi over 15. So using our volume by shell method, we found the exact volume of our solid of revolution was 2 pi over 15, and then whatever the units would end up being, but they'd be cubic units. All right, so we just ran through this example problem using the shell method, but this is actually an example of a solid of revolution that we could find using either method. So I want to quickly run through this example using the washer method and see that we get the exact same answer of 2 pi over 15. And I'm going to run through the washer method pretty quickly because it's one we've seen before. And the whole point is just to show that each method will give us the exact same volume, but in certain circumstances, like we've seen in some other examples, maybe one is easier to calculate than another. All right, so if we're going to be using the disk or washer method, and we have our region rotated around the x-axis, then we're going to want to take a slice that is perpendicular to our axis of rotation. So I'll do this in green. Sorry if it gets a little bit messy here, but I wanted to keep everything up. So now we are taking a vertical slice for our disk or washer method, and the thickness of such a slice would be delta x. So that tells us we're going to write and express everything in terms of the variable x. And my little sketch there is actually a little inaccurate. There should not be that middle region to our rectangle, right? That would be in our slice, but because we end up with an actual washer. So this is our vertical approximating rectangle, and we can think, if we want to, similar to the shell method, as rotating that vertical approximating rectangle around our x-axis or axis of rotation, and that is creating one of our washers. So I'm not that great of an artist, but that's pretty much what our washer is going to look roughly like. And now we have to remember to find the volume using our washer method. What it really comes down to is integrating the area of that cross section. And so, well, how do we find the area of that cross section? Well, if we look at it from the side, we can see that side area is really just the area of a big circle minus the area of the smaller circle. So remember, this formula says we're really just integrating this cross-sectional side area of one of our slices, then doing that for every slice and adding them all up. But what that delta x, or the differential of x, is really telling us is that we're multiplying that cross-sectional area by some thickness, some delta x, and that actually gives us a volume. So we're adding up a bunch of volumes, the volumes of all these kind of hollow cylinders. All right, so to make progress with our washer method, we have to find an expression for the outer radius of our washer as a function of x, as well as an expression for the inner radius of our washer as a function of x. So remember, the x-axis is our axis of rotation. This little green rectangle is the rectangle that we use to generate our washer, just by rotating around our axis of rotation. So you can see that washer is going to have an inner radius given by the difference between the x-axis, or that y value, and this y value at the bottom of our region, and it'll have an outer radius corresponding to the distance from our x-axis to the top of our region. Well, these vertical distances are really just y values, and we can express each of these y values as a function of x using the corresponding formula. So our top y value, which corresponds to our outer radius, is given from the straight line function where y is equal to x. And so if we express that y value as a function of x, we just get x. So our outer radius is going to be just x, but we have to remember we have to square that outer radius. So now to finish setting up our definite integral for our volume using the washer method, we need to find a similar expression as a function of x for the inner radius. Remember, the inner radius is this small little vertical distance from our axis of rotation to the bottom of our region of interest. That vertical distance is again a y value. Remember, y values are vertical. And well, that y value is going to be given by a point on the curve y equals x squared. Well, we know how to express that y value in terms of x when it's on that curve. It's given by x squared. So we have pi times x squared squared. Don't forget to square that x squared, or think of it as x to the fourth. And so to finish setting up our definite integral for our washer method, we still need our limits of integration. Those are all the x values we run through for the original bounded region, which will be from 0 to 1. It's just coincidence that those are the same as the y values. They will not always be the same. All right, so now let's go ahead and find our antiderivative. We're going to get pi x cubed over 3 for that first term. Remember, this is x to the fourth, so we're subtracting away from that. Pi times x to the fifth over 5. We have to evaluate that at 1 and 0 and take the difference. But when we plug in x equals 0, we're going to get nothing. So it really comes down to that upper limit of integration. That'll give us pi over 3 minus pi over 5. But wait a second. If we take the time to write that as a single fraction, find a common denominator and all of that, what do we end up with? Well, you probably already knew. because we already did it, we end up with exactly 2 pi over 15. So no matter how we slice it up or cut it up, as long as we put the pieces back together correctly, we should get the same volume. And that's really nice to see in this example. Either method will give us the exact same volume of 2 pi over 15. So sometimes it doesn't matter which method you use, they'll both work, but in other times you really want to kind of think of maybe setting each up and seeing which integral is going to be easier to evaluate or just easier to set up.